Hello everyone, welcome back. So in the previous video, I discussed about the solution of the third problem of today's weekly contest design memory allocator. In this video, there are like I talked about two different follow-ups. One slight variation of the same problem can be what about what if I can implement allocate in order n and I have to implement free in less than order n, right? And second follow up was what if I can implement free in order n and I have to implement allocate in less than order n, right? So in this video we will be talking about the first variation wherein we will be looking at how to implement free in less than order one in less than order n and uh, the allocate would still be order n or there is an extra log factor n log n or something like that. Okay, so let's jump right into it. So I assume that you already know the problem and you already watched that particular video. The video is very short, it is around 10 minutes and you can watch it easily in 2x. So I would encourage you to at least give the problem a read and understand the solution. Okay, so the solution that we had come up with was we are implementing free something like this. So we okay, just to let's just quickly recap that solution. So the solution was this that if we will for allocate we will start from left to right and we will just find a continuous block of 0. 0 means the current position is free. We'll just find a continuous block of 0. If that continuous block of 0 is greater than the required size of continuous block, we will just allocate them the current with the current ID. Okay. And finally, in the free function, what we are doing, we are just iterating over the entire array again. We are seeing which block has the current ID and we are returning our result based on that. Okay. Now this is what free function was, and now we have to currently it is order n, like you can see it is order n, right? And now we have to reduce this from order n to something less than order n. It will be order 1 or order log n or order root n, something less than order n, right? Now what exactly we are returning from this function? We are returning the number of freed indexes, right? So can we pre-calculate this field index? Like first of all, we need to reduce the time complexity, right? So we can't actually iterate over the entire array. So this entire loop is something we want to get rid of, right? Now, what this loop is doing? This loop is doing two things. One, it is counting the number of free element, and second, it is freeing up that block itself, right? So we need to come up with some approach that will actually do these two things in less than order n time. That's the entire motive, right? Now the first let's take this one by one. Let's say we want to first tackle that. I need to find out what is the number of freed elements. I need this count. Now how can you get this count? So notice that you are iterating, like you still can have order n kind of complexity in allocate, right? And you want the number of freed elements. So can't you just maintain a map here? Like apart from assigning it the ID, you can maintain a map and just say, okay, uh, map of this particular MID plus equals number of plus equals size. Basically, just increase the number of elements with this particular MID by size, right? And we can just return that, but you can use that particular map in free function and we will get rid of this free at all. Like we don't need to do this free now in our loop. So instead of this free, this would be some map of some ID, right? This will be this will give us number of freed elements. Now, second thing that this for loop is doing is actually making these blocks available for reuse, right? So how can we make this work? Like how can we make this work in less than order n? Now, first of all, we can't iterate like this number of blocks that needs to be freed up or this that needs to be assigned to 0 is something that we we can't do without iterating over the entire elements. You can think of some fancy data structure like segment trees and range update there, but we are not going there directly. Like as discussed, we'll start with basics and we will see if we need that particular data structure or not, because segment tree is something which is meant for something else. Like you need to query something, and segmentary gives you query efficiently, and with query you have some updates as well. So that is a scenario where segmentary would be helpful. But in this case, we what we are saying is number of we need to just free up some elements, right? And we need to do it efficiently. Now it is clear that we can't iterate over the entire thing, and if we have to mark each of them as zero, we need to do this. There is no other choice, right? So basically we can't mark these blocks as zero at all. So here comes a very interesting concept that is actually used in solving real life problem as well. So think about this. You can't reuse, like let's say you don't do this. Let's say you don't mark it as zero. So what will happen? This blocks of j would contain some id 1, right? Now this 1 is something which will be used further in the query. So let's say let's talk about this scenario first, and then we will revisit this. So let's say you have allocator 4. So you allocated this 4 as uh, 1, right? You mark everything as 1, right? Now you allocate, next is allocate 4 of 2. So you allocated this 4 and you mark everything here as 2, right? So that is good. Now you want to free 1. So once you want to free 1, you will just okay. So we know that we can get the blocks easily, but we can't actually remove these blocks. Like we can get this count 4 easily for this free function. Like the answer for this free would be 4, and we can get this 4 easily. But we can't actually free up this block. We can't mark this as 0. So now let's say there is different request allocate 2 of 1. So in this case, if we would have freed up this block, if we would have marked this as 0, right? So this block would be considered. But now because these two are 1, we will consider this block as the answer, which is not correct, right? So basically, there can be queries with the same ID, right, or different ID, and those queries can have utilized this free blocks if present. But because we are not freeing up this block at all, these queries returns wrong answers, right? So what exactly you need to do? So first of all, to solve this, can you can you reuse this one at all? Like let's say you know that they are by some magic you know that these are zeros. Like let's just assume this by some magic you know this, right? Now if you know that these are zeros, like this still are one marked as one, but you know somehow that this is zero, like this is free. So now if you allocate two blocks here, can you reuse this one? Because what you are saying is one is free. You are maintaining, let's say you are maintaining a set which contain which all elements are already free. So initially 0 was free, but now you added 1 as well. That 1 is also free. So like if you encounter 1, just consider it as free. Now if you do this, can you, like first of all, can you do this? Like if we do this, we our problem that we are not utilizing this entire piece of uh, continuous block as free. Rather like even then, even if this are marked as 0, so we just solve this particular problem by saying that okay, I will just assume that everything which is marked as 1 is also free. Now can you say this confidently? The answer is no. If there is a request again which says that okay, allocate a block of 2 with id 1, then if you allocate a block of 2, you will find this block free, right? Because you are saying that 0 and 1 both are free. So you will allocate this block to this particular query, and you will try to mark this as 1. Now if you mark this as 1, if you mark this as 1, this would be free. Like this would be reutilized again in the next query. In the next query, you will see that okay, this is 1, so this is free, so I will utilize this. But that is incorrect because this block was already utilized by some other query, right? So basically, by saying that one is free, we are solving one part of the problem where we need to understand that one wherever one is present, that is also free. But because the next queries can also have one, next queries can also have one, we can't really assume that all the ones are zero. So we need to differentiate between the one which was there for previous query and the one which comes for next queries, right? We need to differentiate these two somehow. So this is very standard technique. Like let's say, uh, let's talk about YouTube itself. In YouTube, the my alias is coding moon, right? Now you to me or to you it looks like coding mohan is unique, like coding mohan is a unique channel, but in internal databases, like in internal databases, YouTube might be storing it as some raw IDs like 1 2 3 4 5 6 something like that, right? Like this ID maps to coding mohan, right? So basically internal ID can be different from external ID. Externally it is looking at one, right? It is look like externally this ID is one, but I can map this I can map this one to something internal. Okay, so let's see how to do this. So that's the basic idea. We'll just map it with some internal ID. Like these are the external IDs, and we will try to map this external IDs with some internal IDs. That would make sure that if I can easily determine whether this one was previous one or this one is new one. I can easily determine this. And if we are able to determine this easily, our problem is solved. Like we don't need to mark this blocks as zero. We'll just put one in this free set. Okay. And our definition of free would look then something like this, that if free contains this then it is free. Like if free contains whatever value is there, if free contains this value, then I will understand this block as free. Okay, so if free contains this value, I will make internally I will think, okay, this block is free. Now let's see how we can map this internally and how we can make sure that we are able to differentiate between these two IDs effectively. So let's say you get one, you maintain a map. First of all, internal IDs to external IDs, right? So let's say this is external IDs, right? And this is your internal IDs, right? So uh, now you get one. So once you get one, you will mark this as one. Let's say you are maintaining internal ID counter, like you will just mark internal IDs 1 2 3 4 and so on, right? So initially you got one. For external IDs you mark internal ID as one. Okay, now you got two. So okay, you got two, so you will mark this as two, right? Now let's say you freed up one. So you freed up one, so this one is now gone, right? This mapping is now gone. Again one comes. Let's say one comes. So you, instead of assigning this one the previous internal ID one, you will assign it a new internal ID, which is 3. Now once you assign this a new ID, your entire problem is solved. Think about it. Previously we say that okay, one is now free. So one is free, that is okay. But when we are assigning one again, we are having problem. But now with this internal ID concept, we are making sure that new one, if a new one comes, I will give it a new ID, not the previous ID. So if any ID comes, I am sure that I am giving it a new ID. And because I am giving it a new ID, I can safely assume or safely consider all these indexes as free indexes. Okay, so hope this point makes sense. If it doesn't, I would encourage you to rewind the past minute or two of the video, and you will be able to get it. So what was the problem? The problem we started with saying that okay, we need to remove this for loop. In this for loop we were doing two things. One, we are incrementing the free elements, count of free elements. And second, we are marking it as free, like we are marking that particular block as free. So what we did is we said that okay, this count is something I can get from a map, so I can just maintain a map and I will get the count. That is okay. uh, but marking it as free is something I can't do without iterating over the entire thing, right? So I will just say, okay, instead of marking it as free, I will say everything which was marked as this particular ID, which was marked as particular ID is already free. So I will say, okay, 0 means free. Now 1 also means free. Now once we said that, we are now okay with like our free function. Free function is now order 1 or order login, depending on what kind of map or setter you use. Um, Once our freed function is like optimized, what we need to just make sure is, if a new ID comes again, we we better not reutilize the previous id, because if a new id comes here and we mark or we fill this particular value with 1 itself, then I will consider, the algorithm will consider this as free cells, which is not true, right? So that's where what we did is we just maintain, okay, what is the requirement? Requirement is, if an index comes again, or if something comes, I would map it to a unique internal ID. So that's where we maintain an internal and external ID map. And here we are just making sure that every time we get a new ID, we will just increment the counter of internal ID and assign it a very unique internal ID. So now, if something comes again, I will assign it a new unique ID, and I will fill it with that new unique ID instead of this one. Okay, so let's just do a small dry run on this example, and then we'll look at the code. Okay, so again, I would strongly encourage you to rewind sections of the video to understand concept if you are still not if you are still unclear, uh, because the code is very simple. It just understanding this mapping bit is coming up with this mapping and understanding is the tedious part. And this concept is actually used in a lot of real life problems, as we just discussed about a YouTube case. Other websites also uses same kind of concepts, right? So this is something which you should do, or you should utilize in the real life scenarios as well. Okay, so just to let's just solve this particular problem. So initially everything is 0, right? So let's just remove, sorry, let's just this one is not there, right? Initially 0 is free. 0 means free and everything is marked as 0, right? Initially 0 means free and everything is marked as 0. Now allocate 4 of 1 comes. We'll see whether it is free. Yes, it is free. Find me the continuous block of free elements. You will what is the definition of free? Definition of free is this. Now we will check whether the value here present in this array or not, free array or not. If it is free. So currently we'll see, okay, there is a lot of free elements and it is greater than 4. So we'll just assign the first 4 indexes to this allocate, and return 0, because 0 is the first index which we are assigning. And correspondingly we'll map this 1 to 1, like 1 maps to internal id 1, and we fill this internal id here. We are filling internal id. Now for 2 comes. So again we'll look at this, whether it is free or not. 1 is not there in this, so it is not free. So this one is free, and there is a long length which is free, which is, we can accommodate 4 here. So we just accommodate this 4 from here, right? And return 4 as an answer here. And mark, like the internal id of this is 2, right? So we'll just mark each of these as 2, right? Now a request comes that, okay, free 1. So once we say free 1, we know the count because we are maintaining the count somewhere, let's say. So we know the count, we return 4 from here. But apart from returning 4, we will just see what was the value here. The value here was, like, the value we are freeing up is 1, and 1 maps to internal id 1. So we'll just say that 1 internal id 1 is now free. So again, internal id 1 is now free, not external id. And we'll remove this mapping as well, so that we know that there is no mapping for 1. Now again, this allocate request come to our like 2 cells of 1. So now you will try to find the continuous free block. So now 1 is also considered as free. So we'll have 4 continuous block here, and we want 2 blocks, so satisfied. So we will just mark this 2 as 3. Now why 3? Because the internal id of this 1 is now 3, right? Again a request come 3 or 5. So internal id of 1 is 3 only. So we'll reuse this 3, and we want 3 blocks. So If you start from here, there are two blocks free, so this is not correct. So we'll just mark these three blocks as internal ID 3. Okay. Now let's say another request come. Let's just take the last example. Let's say another request come free 1. Again free 1. So 1 is mapped to 3, right? So we will free up 3. Or in other words, we will say 3 is also considered as free and return the map, like the map of 3, the value which were marked as 3, which is 5. Okay, so hope this entire process makes sense. Let's look at the code quickly. So the code is very similar. This is the is-free function that we are talking about, and as we said, we maintain three things: one, external to internal ID map; second, internal ID to size map, like to answer this 4 and 5, this free queries; and third, the set of free internal IDs. Now, each free function would just check whether the value is present in this set or not. If it is, then it is considered as free. So initially we just insert 0 because 0 is considered as free, and internal ID counter is 1. Like there is, if something arrives, I will give it a counter of 1. I get a value of 1. Now let's look at the allocate function. So allocate function is saying that okay, I will find out the internal ID first. So this is finding the internal ID, and if it is not present, like if id is 0, I will just assign a new internal id. Now after I found the internal id, I will find a continuous block. So we'll just check whether, like this, previously this was equals to 0, block of j not equals to 0, block of j equals to 0. It is just now replaced with is free, right? And this entire thing is same. Now if continuous block of free size is greater than the required size, we will fill this with internal id, not with the mid that we got. We'll fill it with internal id, and we will just increment the value of that particular id, the count of indexes of that particular id with this size, and return the start. Okay, so this is exactly similar. Free is a little bit different. What we are seeing is if this ID is present in our map or not. If it is not, we return 0. Okay. If it is present in our map, then it means we have some elements which are assigned with this external ID. So we'll find the internal ID, corresponding internal ID. We will remove this from our map. Remember, we are removing this entry, right? So that if anytime new ones come, we will assign a new ID. So we'll remove this from our map and insert it in our free array, right? And finally, we will just return this answer, internal ID to size. Now, notice that we don't need to erase this here. We can erase this or we can't erase this. It doesn't matter because ID is the internal ID and it will be new for every follow-up request with the same external ID. Okay. So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. Again, there is uh, one more interesting variation of the problem which is left out, in which we have to make allocate faster and free can be slow as well. So I would encourage you to solve that problem by yourself as an exercise. And if you need any help or suggestion on that particular problem, feel free to post that in the comment section below. I would be able to do that. So with that, if you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. And I will see you in the next week. Thank you.